Okay, so let's get started. This will be a sort of shorter class um, because we are just going to be looking at code and how to look at things, how to use word embeddings, and so on. So this is a tutorial I found on Colab, and I think it is a student's homework of the Stanford um, tutorial. Not very sure, but I was just googling embedding tutorials and I found this quite good, and I've used that. I could not see the author, so yeah, please forgive me for that. I have shared this, so if you log in with your CSC SSN ID, you should be able to access it and make a local copy and make changes. Please don't make changes on this. I don't know if I've given you editing permission, but yes, I will look into that. So let's get started. What are we going to do today? We're basically going to explore word2vec, see how different or how useful they are for tasks, and see some application of the same. So first, I have already installed Spacey and a language model, which is basically words and its vectors and so on. So we just get, first of all, are all of you comfortable with Python?
Yes, ma'am.
Okay,
Yes, ma'am.
good. Okay. So I am not very comfortable with Python, but I have the general idea of that, and I had already downloaded this. I don't know why this has not happened, but anyway, please just give me a moment. So anyway, I'll look over the code. We'll be importing the Spacey and language model, and we'll also be importing some learning statistics so that you can measure how good it is on an extrinsic task, as we said before. And TSNE is a visualization technique, as I said before, for high dimensional vectors. And yeah, look into that. Okay, first we will load the model. We have different models, say built from Wikipedia or other sources of text. I'm just using one of them. And then what we'll be doing is looking at the vectorial representation. So this is the advantage of using the pre-trained vectors, that I don't have to actually train the vectorial representation. And we already saw what is cosine similarity, and we'll be measuring that. So first, we just retrieve a few words and see what the vectorial representations are. So first, this particular language model has vector size 300. And I just printed one of them. And yeah, you can see it has positive values, negative values. So basically, anything that the weight vector can take can be the value. So what this also means is that the various dimensions of this vector are not interpretable. And that is a drawback we'll be seeing later on. But yeah, right now this is how it looks like. Now we take any other word and check the dimension. It has to be 300 because that is how the training would have happened. Your hidden layer would have been of size 300. Now, there is an inbuilt function in Spacey to measure the similarity, and it's just this word dot similarity and other words. And you can say cat and cat is one, cat and dog is highly similar. Dog and cat is same as cat and dog because we know cosine similarity function is just multiplication. So it is going to be symmetric, whether it's cat and dog or dog and cat. And it's going to be between 0 and 1 because we have normalized it. And the similarity between cat and car is much reduced. And these are the interesting and useful features we have for word vectors. Now, we have the cosine similarity between hotel and motel, and motel and hospital. So hotel similarity with motel is 0.784, but hotel and hospital is less. Now this is an interesting example because if you see the characters between hotel and hospital, they're quite similar. Now we had looked at Jacquard similarity before, where we'll basically take the intersection and union. So if I did Jacquard similarity here, I actually get a high score because H, O, T and L are there in both. But here we get the semantic similarity that hotel and motel is more similar than hotel and hospital. Whereas in Jacquard similarity, both of them would have been equally similar because we have four characters that are similar in both. So that is the importance of analyzing this. Maybe I should make a note here. Um, compare with. Okay, so instead of using the inbuilt similarity, we can even compute it because it's quite straightforward. You use the numpy module which has all the array functions, and you basically take the dot product and divide by the product of the norm, and you get the exact same 0.356 we saw here earlier. Now we saw how to compare two words with the pre-trained vector, and now the interesting thing is we'll now look at all the analogy functions where we have to retrieve or things like that. So we define a function called similar. So I'm going to quickly go through the words in the vocabulary, and this is basically all the vectors and the words, and then I'm going to sort based on their similarity. So it's going to be sorted in the sense the most similar is going to be on the first and return. So I'll just run that. And the reason I'm using that W is lower is because if I don't use that, I'll be getting various spellings of the same. So the thing about Word2Vec is that it is not trained on a cleaned dataset. In the sense, we don't do tokenization or normalization or anything like that. And that is important because in our slide, if you remember, we saw things like Cu is to copper as Au is to gold. Now, those kind of things wouldn't have been captured if we just completely converted everything to lowercase, right? So, the choice has been taken to include capital letters and all kinds of exclamation and so on and so forth, so that we capture this information. So that also that our vocabulary is inflated by all these various spellings. So that is also something to note. So when we retrieve words similar to cat, it's going to take time because first of all, we are going to be having this all words computation here. Of course, to optimize it, you can put it somewhere else so that it's calculated once and for all and just refer it. So we see cat is similar to cat, cats, kitten, dog, kitty, pet, puppy, kittens, feline, and dogs. And here we have retrieved 10 top values. So we can retrieve, say, 20 and see what happens. So we start getting other pets we get rabbit and bunny and hamster and cat. And you can imagine it's trained on some, you know, on some data set where um, pets such as rabbits and hamsters are uh, popular and things like that. So, like fish hasn't come up yet, as we can see. So anyway, so that's the interesting thing. Though it calculated, it retrieved all the words from the dictionary. That's because we're just reading it. We're not training anything. So this was retrieval and similarity. Now we'll come to analogy. So as we saw before, man is to woman as king is to queen basically implies the difference between them as similar. So you have male, female, verb tense, country, capital, and so on. So we take the word king, man, and woman, and we take the result king minus man plus woman, and we have this cosine function. Of course, you can use the no, here you cannot use the inbuilt function because you are creating a vector. So the hash function works like word. Given a word, you have a vector. You don't have a hash function to give a vector and retrieve a word. And it also doesn't make sense because we cannot say that this particular vector will represent a word. Maximum what we can say is this is the closest vector we get. So here we are forced to define our own cosine function. And we'll be saying how close the word queen is to the result. They say around 0.78, and it's quite similar. Then what we do is we retrieve words that are similar in the sense we take all the words where and we remove the king, man, and woman, and then we see the words closest to this result vector. So we computed result here, which was king minus man plus woman, and then we retrieve all the words that are closest to result. The reason we are removing king, man, and woman is, of course, because it is in this representation. And again, we have printed the first five. What are the top five? So we can see queen, prince, king, princess, royal, and so on. And yeah, let's try the same for Paris minus France is Madrid minus Spain. So I take the vectors for Paris, France, and Madrid, and then I remove the words from the vocabulary, and then we should get Spain. So we get Spain, Barcelona, Argentina, Valencia, and España. So these are the top related to the difference. And as I said before, it's because Word2Vec does capture a linear relationship, which might not be the case in other vectorial representations. Now we come to sentence and document similarity, where we use the word embeddings to calculate similarity between sentences and documents. Of course, you can use Doc2Vec or neural networks, but here we continue to use Word2Vec. So we are going to calculate the similarity between these sentences, which is cats are beautiful animals, some gorgeous creatures are felines, and dolphins are swimming mammals. This implementation is, of course, a very naive implementation where you just add the words manually, but you can come up with a better coding to just take input as a sentence and return a vectorial representation, and then the cosine similarity. So cosine similarity here is 0.91 for these two. And you can imagine because we have cats, we have felines, we have animals, we have creatures, we have beautiful, we have gorgeous. So these two sentences are intuitively quite similar. And these two are also quite high, though because of the semantics that felines are mammals and dolphins are creatures. So it's 0.78. And this is something, the similarity between the second and the third sentence is something we would not have captured in LSA, we would not have captured in one hot encoding for sure, because none of the words except R are repeating. And that is the uh, beauty of this. And Spacey also supports sentence evaluation. It does the same thing, and we get the same value basically for the same. Now we come to visualization, and we are using Disney. I've added a link to Disney in the reading material. You can go through that. We'll not be covering it in this course. And here what you do is you take the number of components and say king, man, queen, woman, and then you plot it basically. So yeah, it gives us a nice thing that the distance between man and woman is quite similar to king and queen, and that's what we were going for. And this is one of the successful examples. So you will see this example in every piece of like literature that refers to word embeddings. Next, so this is till now what we saw is the intrinsic evaluation. We saw we saw similarity using cosine similarity. We saw analogy. We also saw sentence similarity. So these are some examples of intrinsic evaluation. Now we come to, we also saw visualization, so that's also an intrinsic evaluation. But you can imagine if your analogy has worked out, your visualization is also going to work out. But it's always much easier to convince people once you have a visualization. So now we come to an extrinsic evaluation where I use sentiment analysis to describe the power of word vectors. So here what we're going to do is we're going to use a logistic regression to do sentiment analysis, and we just have 0 or 1 sentiment. So oh no, I have to download this. Okay, just a minute. Okay, so our training, our data is going to be basically having a sentence and the label 0 or 1. So that is a binary classification, which is what logistic regression is good at. I mean, it's designed for it, not good at. It can only do binary classification. So yes, have you learned logistic regression in your machine learning course?
Yes, ma'am.
Okay. So, as you might know, this is only for binary classification, and though it's called logistic regression, it's not a regression algorithm. Okay, thank you. So yes, I've uploaded the data set. It has a lot of sentences and a label 0 or 1. I'm just examining the data. It has 2748 examples, and then if I hadn't wasted enough of my life, this poured salt in my wound. So that's a negative statement, clearly. Okay, let me do for 2000 first. So this is a very naive way of splitting the data. I've basically taken the first 2000 entries as the training and the last 748 as the testing. A better way of doing this would, of course, be using random splits for this, averaging across splits. But right now, our focus is on word embeddings, not machine learning. So we'll take this naive method. So let's just see the dimensions, whether we've got it right. taking some time because we are going through all the data and creating this train test split. Okay, so our training set is of size 2000. We have our logistic regression, and then we predict and print the accuracy. You can see it's pretty good. It has around 86%. So it does well on an extrinsic task. And then we print the confusion metrics for this. So you can see that it is misclassifying a bit, and yeah, we can have the precision, the recall, the F1 score, and so on and so forth. Now you can take a higher number of training examples. So if I take 2500, what would be the remaining? And 248. Okay. Okay. So if I train this, I get a similar score. What was it before? So I took it off. But yeah, so the misclassifications are a bit less, but of course the training size is also less. But what I'm trying to say is that the even in extrinsic evaluation, the quality of your results is directly proportional to how big your input data is. Though it is not as severe as in the case of deep learning, you do need to have large amounts of data to see the usefulness of word vectors. And that is, of course, a roadblock for domain specific things. So, for example, in sentiment analysis, when you have Amazon reviews or something like that, you have such kind of data sets where it's just data explosion and you don't know what to do with the data, then it works very well. But if you have very small, very niche data sets, then word vectors, um, the advantage of word vectors is because it's pre-trained on other data sets, you can still use it to good effect, but it is not interpretable and the quality of the result improves anyway with more data. So that was the point I was trying to make. And yeah, we are done with the tutorial. And if you have any questions, you can ask. And yes, today has been a short class, but I didn't want to go ahead with the next topic today. So let me know.
Ma'am, I had one doubt.
Yeah. Yeah.
Here in this sentence level similarity,
Okay.
the similarity is like of the sentence's meanings or the words in the sentence. Like, for
So
example,
here, yeah, tell me.
like if there are two sentences, for
Okay.
this S1 and S2 are two sentences, they can have the same words and different meanings. So, like,
Okay. You mean to say homonymy, basically. That is, you're having the same words, but they mean different. How will you
mean
capture
different.
that?
Yes, ma'am.
Okay.
So, what will be the result now? Like, will it give one as the score or some low value
You tell
for
me,
side.
this is what is happening. In sentence similarity, we are summing up the word vectors. I'm basically taking the average of the words, right? So if I have
Yes,
two
ma'am.
sentences, cats are beautiful animals, and um, if all the words in the second sentence are exactly the same,
Exactly the same, but the meaning is different. And I think that it will give one or high
yeah,
value as
no, no, it will
this
give one only because for a
one.
word there is only one vector. Okay. In Word2Vec, when I retrieve, so when I say, okay, NLP dot, okay, I'll go back to cat here. Okay, I'll go back to the very beginning. So when I retrieve the word vector for cat, I have this particular huge vector, right? So it
Yes,
doesn't depend on which meaning it is. Uh, I just get one vector. So if I have different meanings, it's still going to retrieve the same. But
so
when I said, yeah, continue.
it's just a point in the space. Uh,
Exactly, it's just a point. And that's why it's a vector in the sense it's a representation,
okay,
right?
yes, ma'am.
Yeah, so it's just a point. So if you have two sentences which have exactly the same words, it's going to take one. But also, this is a very theoretical example, right? You're not going to have two sentences which have exactly same set of words. If two words have different meaning, probably your sentence will have words that justify the different meaning.
Yes,
So in real life, that it it does differentiate the sentence similarity. But you are right. If you have two exactly same sentences with the same words, your similarity is going to be one because you're taking the sum of the vectors and taking the average. So it's nothing. You're
yes,
not having multiple meanings, which is why in the end of the last lecture, I was telling we'll be looking at contextualized embeddings, which is given a word and a context, you will get different embeddings. We'll be looking at that in the later in the course. But word to vec is not a contextualized embedding. It is the vector itself contains information that it can mean different things. But when you use it in a sentence, you use only one vector.
okay.
Okay. So
Ma'am,
if
and
you have, yeah,
yes,
let me just
no, no,
finish this. I'll come back to
yes,
that.
ma'am.
If you have different meanings, same word having different meanings, um, tell me some word, maybe it'll be easier for me to explain.
Ma'am,
Um,
I can
I'm
think
not
of one
getting
sentence
it.
like
Yeah,
like
tell me.
uh, a dog bites man and man
Hmm.
bites dog. Like they have the same
Oh,
words
okay.
but different meanings.
Yeah,
Like
yeah, yeah. Well, that's not captured. That's a very good point. Even though the word meanings are the same, because the order is different, in the sentence similarity, it is not captured. But in Doc2Vec, which we saw, it is captured because there our task was to identify the next word. So, man bites dog would have been man bites, and you have to predict dog. And the other sentence, dog bites man, would have been after dog bites, you have to predict man.
man.
So in dog to egg, that similarity is captured, and that's one of the biggest. You raised an interesting point in the sense it's one of the biggest drawbacks of averaging anything, because when you average something, so, say if you're averaging 5 words is okay, but if you're averaging some 20 words, all your documents, all your vectors are going to be very similar because a lot of words are going to repeat. So that's why
Yes,
doctor work and other things are
averaging.
important.
Yes,
Okay.
thank you,
You had
ma'am.
another question?
Not a question, ma'am. This you uploaded this combined training text, no?
Ah,
Where can
yeah.
I get?
Yeah. It's there in the it's there in the description I've given it. So here,
Oh,
this
there's a
combined,
link. Yes,
there's
yes.
a link there. You can just download and upload and see.
Okay, thank you.
Okay, thank you. Yeah. Any other questions?
Ma'am, kind of going back to what Ayush asked.
Okay.
So, like, when you were talking about the doc to X, so like,
Mm-hmm.
the basic difference in like the examples that he gave was like the part of speech, right? So, does doc to X like incorporate that in any way? Like comparing if there's two sentences, giving a similarity by comparing the parts of speech of like the two of them.
Mm-hmm.
Like, are the nouns
No,
similar? Are the verbs similar?
actually, part of speech is same for both because they're all nouns only, right? At the end of the day, whether man or dog or
Yeah,
something.
yeah,
It's
but like,
actually the difference is the sequence. It's not the
okay,
part of speech. So, dog to a capture sequence because we are not only interested in word and the context. What we're interested is also the sequence because okay, I'll stop sharing this and go back to the presentation. Just give me a minute. Um, Okay. So in Doc2X, we are interested in predicting the next word, not just context or middle. So in context or middle, what happens is I told you about wait time, right? That all the context words have similar weight and all the center words have similar weight. So there, that kind of averaging happens. But here, all of these have separate weights. So what we do is that we capture the sequence information. So the cat sat and then you want to predict on. So that is captured in Doctor. Um, but part of speech is an interesting question because part of speech uh, is being captured by word to vec because of context. Though it is not explicitly being fed into the system, like no parse tree is being fed or any annotated data is not being fed, but by virtue of the context information, if you try and do these analogy tasks for similar part of speech and so on, or you use it to classify and build a model for part of speech, it does very well. And the same thing is being captured by Dr. Weck because it's a very similar architecture. It's only building up on top of that. I hope that answered your question, Aarti.
yes, ma'am. Yeah.
Okay. Yes. Um, do you find it interesting in general to the whole class? And,
Yes.
okay.
Yes, ma'am.
Yeah.